Okay, students, so we have understood the importance of what? Closure set of attributes. Why they are important? Because they help in identifying the keys. So what is the application of what? Closure set of attributes. The very famous or the very important application of closure set of attributes is it helps in determining what a candidate keys using the attribute closures, using the attribute closure. Let's quickly recap or recall the definition of a candidate key. What is a candidate key? It's candidate key. It's a candidate key. So what is a candidate key? It's a minimal set of attributes. So remember, what we have is we have super key, then we have key, then we have candidate keys, it's a plural word, and then from them we have primary key, then we have the alternate key, and we can have a surrogate key or an artificial key also. Then we can have a compound key also. Yes, so all of these types of keys, I think all of you remember that. So candidate key is a key only because it's a singular term. Otherwise the candidate keys are there, which is a plural term. So what is a candidate key? It's a minimal set of attributes that uniquely identifies every tuple in a relation, that uniquely identify every tuple in a relation. And the second property is that it is irreducible. It is irreducible. What is the meaning of irreducible? No proper subset can still uniquely identify the tuples. That means it should not be a super key, because super key extra attributes are added, and those extra attributes we remove them and we try to make it minimal. That's why the word minimal is there. Remember, the word minimum is different. This is minimal. So let's see an example. Okay, what is a super key and what is a candidate key in this case? But the main thing is that the attributes are required in that, and from the attributes we can find out the closures, and from the you know what is required for the closure? Functional dependencies are required. Let's see first the algorithm or a simple systematic step to find out the candidate key using closure. So first, find the attribute closure for each attribute set. And we know that how this is the last algorithm that you need to use in this first step. Calculate x plus closure of a x for the subsets of the attribute using functional dependency. So the last algorithm, you have to call it here as a function in first step. Check if x cover all the attributes. So it should cover all the attributes. This is one check in second step we are using. If x plus include all the attribute in a relation, that means x plus is equal to all attributes, then x is a super key. We can say that x is a super key. Then the third step is a systematic approach. Third step is what? A super key is a candidate key if no proper subset of x is a super key. What is the meaning here? For example, let's see a proper example here. Okay, I will not confuse you guys. So let's see a proper example. Three steps are clear. The first step is what? It's a previous algorithm we are calling here. So if you are making a previous algorithm as a function, so you can call it here. You can write a program also in Python or in Java. It's not a big deal. Right now, it's not a big deal for you guys. Then check if x covers all the attributes or not. If it is covering all the attributes, then we have to go for the minimality test. So if it is a minimal, then a super key is what? A candidate key. With this condition, no proper subset of x is a super key. So example we are taking here as a relation R having A, B, C, and D. And what are the functional dependencies? These are the functional dependencies. A determine B, and B determine C, and AC determine D. AC determine D. So what is the first step here, student? Calculate closure. So we'll call the previous algorithm. So from this, I can write it here quickly. I will recalculate it, but all of you can understand that. Okay, this is giving all the attributes. So A is giving A, and from this A is giving B also, and from this functional dependency B is giving C, so I can C also, and here I can see A is there and C is there, so I can use this functional dependency also. So I would write D also here. I would write D also here. Then A plus is giving all the attributes. Okay, so we can call it a super key. Right now we can call it a super key. Then the second step is what? In first step, the second iteration is what? B plus. So if you're trying to calculate B plus, B will come, and from B is giving C, only C will come. So here, because A is not there, so we cannot use this functional dependency. So B plus is only giving what? B and C. So B is not a super key, so we are going to reject this. We are going to reject this. Then the third step is what? We will take AC also. Yes, AC also. So if you're taking AC, then AC plus is giving what? This is multiple attributes are there. Obviously, it will give A and C, and from A it will give B also, and from B it will give C because C is already there. So now you can use it AC, and AC is giving what? D. Okay, so AC is also becoming what? A super key. So now we have identified A is a super key, and AC is also a super key. AC is also a super key. Now, if I remove this A, so alone C is determining what? C is determining only C. So it's not a key, it's not even a super key. So I cannot delete this A part. But in AC, if I delete C part, so A is giving what? A is giving, we have already computed A, B, C, and D. So this is A is giving us A, B, C, and D. So we can say that A is minimal in this case. Now, again, if I remove further A, it will become phi or null. And phi and null closure set is not possible because zero attributes would be there. So we started deleting. Okay, I'll give you one more example. If let's say you have A, B, C here. So A, B, C, obviously it's a super key. Super key. So you start deleting C. Still, it is giving all the attributes. Still, it is giving all the attributes. AB is giving all the attributes. Now, can you delete B also? Yes, you can delete B also. Still, it is giving all the attributes. So this A is what? A minimal super key. A is what? A minimal super key. And when it is a minimal super key, we will call it a key or a candidate key. So in some books, they are calling a key, especially in our textbook, they are calling a key, but in most of the other books, they are calling a candidate key with no plurals, with only singular, with only singular. Okay, refer to the key lecture. So there you will find the main difference between a candidate key and a super key also. I hope here it is making sense, and here everything is clear with this algorithm. So from step one, obviously, A and AC are the super keys. So here you don't have to further investigate. Minimal super key is what? A. So there is only one candidate key, which is what? A, which is A. We have computed this one. Can I go with different example? One more example I will take, and we'll try to understand further about the candidate key. So the functional dependencies I'm taking here is AB is determining C, and B is determining what? D, and C is determining what? E, and one more functional dependency is there. D is determining what? A. D is determining A. So the question is simple question. You have to find out whether B is a candidate key or not. B is a candidate key or not. So for this kind of a question, you can write it also. Find out with these set of functional dependency whether B is a candidate key or not. Even relation is not required in that. I'll tell you why relation is not required in this. So I'll start with B plus, and B plus B will give. And from this, I can use this functional dependency, and I can write it D here. Yes, I can write it D here. And from this, I can use this functional dependency, and I can write it A here, A here. Then can I use any other functional dependency also? Any other functional dependency? Yes, I can use A and B combinedly. Why? Because AB is determining C. So in next step, I can write it B, D, A, and C also, because AB combinedly determining what? C. Can I use any other functional dependency? Yes, I can use now is this C functional dependency, which is giving us E. So two things are over here. First, all the lists are exhausted, all the functional dependencies we have used. Plus the other thing is that it is included, or it has included all the attributes. How can we find out all the attributes are there? A is different, B is different, C is different, then D is different, and then E is different. So 5 attributes are there. So B plus is giving us A, B, C, D, E, right? So then we can call it B is what? A candidate key. We can call it B is what? A candidate key. So this way, students, you can find out the candidate key, or you can compute the candidate keys. So what is required to recap? Obviously, first thing is the functional dependencies. Then you need to find out closure, which is represented by plus, and then from this closure set of attributes, you can find out the candidate keys.